Picking up where we left off last time, considering the charges and E fields and their relations, we discussed a plane of charge and realize that a plane of charge produces a constant electric field. And so that leads us to a practical electronics component, which is a capacitor, which when charged, it has parallel conducting plates that have equal and opposite charges. So more on that later, but for now, that's all it is two charge plates. And we know that the E field is perpendicular to the plates. We know it goes from positive to negative, so away from the positive and toward the negative plate. Now, there's the electric field represented, along with the fringe effects at the end, which we don't have to worry about. So if it's truly an infinite plate, you don't have these fringing effects, but from charge stopping at this point. In any case, considering what's going on in the main region here. All right, this is the electric field produced by this positively charged plate, which, by the way, has positive charges all throughout the sheet, not just right here. Think of this as just representative of what's over the entire sheet. So there's E, and it's plus, and of course then it points away from the plate. Now it's uniform everywhere in space, and so it's away from the plate on this side, but a little further away, it's still away from the plate, so it's the same size and direction here as here. And then forget about the negative plate for a minute. We can go even further away from the plate and still discover that the E field is constant. So all these vectors, these E field vectors, are from the positively charged plate. And I want to now do the same thing for the negative plate. And the E field produced by that charge distribution always points toward it, because it's the direction of force on a positive charge. So outside it's pointing in, inside it's just always pointing toward, okay? And the E field from this plate being negative of this size toward the plate here, over here it's going to be the same thing again, because the E field is constant no matter how far away from the plate you get. And then on the other side of the positive plate, it's likewise still the same size. So there's a good representation of the E fields at the different locations from the two plates. And since it's a vector and we add them up outside of the plate, guess what we get? Did you guess? You guessed right. And on the other side, again, the E field is 0. So that's really useful. Outside of the plate, outside of the capacitor, there's no E field. Now inside, we see constructive E field lines. So both the E field from the positive and negative plates are going in the same direction, producing one large E field inside the capacitor. So the electric field is contained inside the capacitor. It's not existing outside, which could wreak all kinds of havoc on other electronic items that are used in our technology. So the fields cancel outside but reinforce inside. And now let me discuss perhaps a little bit different idea, but a hollow sphere that's charged and conducting. So here we have a conducting sphere, positive charge distributed around it. And I'm showing some geometry here that can be replicated anywhere inside this region, drawing these lines that go through the point and intersect on both sides. So I picked this location to be this point here. So it's D on this side and twice the distance over here. Now we have a patch of charge, and we'll call that Q. And then that Q is a small patch. It produces an electric field based on the inverse square law to the right, which is KQ over D squared. And now over on the other side, we're going to fill in this whole region with well, we're just going to consider the region circumscribed by the cone that this really represents. If you put your eyeball over here and look this way, you see a circular region, because this whole thing is a cross-section of a sphere. It's not a circle. Okay, well, what you're seeing is a circle, but it represents a cross-section of a sphere. So putting your eyeball over here, you see in this direction. Of course, hopefully you realize the radius has doubled. And so it's not just twice the charge, it's 4 times. So 4q compared to the original q. Now, that produces an E field to the left. And what's its size? It's k4q over 2d squared, which gives us k4q over 4d squared, which is kq over d squared, which is E right. So the left and the right E fields are the same, and you know what that means. They're equal magnitude, opposite direction. They're going to cancel everywhere inside that hollow sphere. So the E field inside a hollow charge conducting sphere is 0 everywhere. And that's a pretty interesting result. The same result we get from a hollow earth. If you have a hollow earth and you're inside, then you have a 0G field everywhere. You not only feel weightless, but you are weightless. So if you find yourself in that condition, floating around inside a hollowed out earth, you probably want to pinch yourself to wake yourself up. So we'll finish our discussion of charge distributions and the associated electric fields by considering a volume of charge where the charge is distributed uniformly throughout the whole thing. All right, it's not distributed on the outer edge. It's all uniform, kind of like uniform mass in a sphere. Okay. Now, this is kind of interesting. We'll consider the region radius big R. And we're going to consider, so what we want to do is we're inside this thing. It's no longer a hollow sphere of charge. It's a solid sphere of charge, so to speak. And we want to know what the electric field is like inside here. So we're going to consider what it is at small r. Okay, at small r, what is the electric field? Well, from our previous discussion, inside a hollow conducting sphere, this is the same kind of model. It's not conducting, but we have all the charge outside of us. Then inside, there's no electric field. So the shell above little r, this sphere bounded that is of radius r, that shell outside of that does not contribute to the E field, that we find inside. All right. Now, this is, we'll consider Q to be the amount of charge that's bounded by this sphere of radius r. And we define rho not as momentum right now, but volume charge density. So volume charge density is simply charge per volume, charge over volume. That's the density of the charge. Okay, so that's the whole amount of charge, which is big Q, over 4/3 pi r cubed, the volume of the sphere. Now, what would be the charge Q inside little r? In other words, little q inside little r. Well, it's the density of charge, the volume charge density, times the volume. In other words, charge per volume times volume is charge. So that'll give us charge. So here it is, the volume charge density, the number of coulombs per cubic meter, basically, times the volume, or the cubic meters. Well, the volume of sphere little r is just 4/3 pi little r cubed. And so putting that together, we have some cancellation. The constants go away, and we have q little r cubed over big R cubed. So that is the amount of charge bounded by this sphere of radius r. Now the volume of charge inside r looks like a point charge at the center. So if we cram all of Q right at a point here and look outside of that, it acts as though it can be modeled as the same effect as having, again, all the charge concentrated at the center. So hopefully that made a little sense. This charge region is equivalent to having all the charge Q concentrated at the center. And because of that, it is subject to the inverse square law. In other words, E as a function of R is KQ over R squared. And that's K over R squared, but times the amount of charge, which then is what we got before, which is Q R cubed over R cubed. All right. Now, I probably should just clarify what I said a bit ago, namely that this electric field is a function of R. If we put all the charge in the center, then when we go away from this, it's KQ over R squared. But if R, say, is bigger than this bounded region, but you just consider the bounded region, then all the regions outside of it, it has this same formula. And this is just a representative example. We could have put that dotted line real close and then considered everything outside of that. That region looks like a point charge concentrated at the center. Okay, enough on that. As we look at our result, E is a function of R, we notice some cancellation. But before we cancel it, let's recognize that this R cubed occurred because the amount of charge enclosed, this is the charge Q inside R, the amount of charge enclosed is proportional to the volume, and the volume is proportional to the radius to the third power. But it's also subject to the inverse square law as we move from the center outwards. This inverse R squared is a result of the divergence in three-dimensional space from a point charge, the inverse square law. And so two of those R's cancel with this, giving us a net result of KQ little r over big R cubed, realizing that big R cubed is a constant in this problem. So, interesting. R is in the numerator now, so the electric field from a volume of charge is proportional to the radius, which is the same thing we got for gravity. Gravity increased uniformly from, if we burrow a hole down here, from the center on out to the edge, it increases uniformly, just like the E field does here. If we were going to graph this, E is a function of R. It goes uniformly increases till it gets to the outer edge. And then the value is KQR over R cubed. The R in question is big R then. And so it's just, yes, it looks like a point charge at that point, you know, at that location and beyond. Looks like a point charge, all the charge concentrated at the center. Now, as we go outside then, E is KQ over little r squared, which is now exceeded big R. Okay, we're way out here. And so it's just this normal inverse square law that we're familiar with. So that's about enough fun physics corresponding to charge distributions, and we will leave it at that for now.